Good morning, sir.
Good morning.
Good evening.
Good morning, sir.
Good morning.
Good evening, sir. Good night. Good evening, sir. Good night.
Okay.
Good night, sir.
Okay. Very good evening to all of you. Thank you very much for attending this session of the STEMS lecture series. I'm Anirudh, a BSc second year student at Chennai Mathematical Institute. So it is indeed a pleasure introducing Professor Abhay Ashtekar. Professor Abhay Ashtekar is currently the director of very good evening to all of you. Thank you very much for attending this session of the STEMS lecture series. Is the director of the Institute of the Gravitation and the Cosmos, Pennsylvania, USA. He is also the Pugh Professor of the Penn State and the holder of the Eberly Chair. He is well known for the Ashtekar variables and his work in loop quantum gravity, an idea unifying quantum physics and gravity. He completed his PhD at the prestigious University of Chicago. He has then went on to hold various positions, including at Paris, Syracuse, and in India. Professor Ashtekar has authored and co-authored hundreds of scientific papers and has also written or co-edited many scientific books on cosmology, quantum gravity, and general relativity. He was also the former president of the International Society of the General Relativity and Gravitation, and also a former chair of what is now the Division of Gravitational Physics of the American Physical Society. Just a quick instruction before I hand over to Professor Ashtekar. So please use the chat box for your questions during the talk. It'll make it a bit easier, and we'll post it to him either at the end or when the time is appropriate during the talk. So today we will go through an exciting journey, learning more about black holes and their history, and we'll also touch upon 2020's Nobel Prize in Physics, awarded to Dr. Roger Penrose. So I hope all of you enjoy. Over to you, Professor.
All right. So good evening to everybody. And as we just heard, we're going to talk about. I'm going to tell you about black holes and particularly their curious history, and then a little bit about why it took so long for the notion of black holes to be recognized, and what it led finally to is this 2020 Nobel Prize. Okay, so let's go on. The organization of this talk is going to be in these 4 parts, and I will also stop for a couple of minutes at the end of each of these parts so that if there are questions, I can answer them. So if you have questions as I go along, please write them in the chat box so they can be directed to me. So the first part is going to be very simple. It is just Newtonian gravity that I believe all of you know. And in fact, long time ago, people thought that black holes actually existed just using Newtonian gravity. However, we'll see that this is not really true. And this is something that you hear about a lot of time, but that's not really correct. And I will explain why. So why general relativity is really essential for the notion of black holes. And then we'll see that I'll tell you a few words about general relativity, what you need to understand. And then I'll go on to the curious history of black holes. And then finally, the Nobel Prize. Okay, so this is really very elementary stuff. So I'm just telling you about a kind of Newtonian gravity. I hope you know all about it. So think about a small mass m, like a tennis ball, for example. And supposing you throw it up in the gravitational field of the Earth, like a heavy mass m up here, then you know what happens, right? The ball just rises up to a certain time, and then it comes back. So at the turning point, it has a 0 velocity, and then it falls back. So the total energy of the ball is given by the kinetic energy, which is a kinetic energy, and plus the potential energy. But because the ball is bound to Earth, the potential energy is negative and is given by Newton's constant times the mass of Earth times the mass of the ball divided by r. And here v is the velocity of the ball. mv. V here is the velocity of the ball, and little m is the mass of the ball. Okay. Now, the point is that at the very tippy top, where the ball is going to come back, its velocity is 0. And then, therefore, the total energy is going to be at that tippy top point going to be negative, and that is going to be the turning point of this R. But now, supposing, in fact, I give it so much velocity that the total energy up here is actually 0. If the total energy is 0, and you know, all of you, that the energy is conserved as the ball is going up and down, the energy is conserved. But if the total energy is 0, and this energy is conserved. So supposing the ball actually then goes out all the way to infinity. If it goes all the way to infinity, R is infinite, and therefore this term goes away. And therefore, really only at infinity, the velocity of the ball would be equal to the velocity of the ball would be 0. So if you like, the turning point is really at infinity. This means that the ball actually can escape and go out all the way to infinity. So E equal to 0 is the equation which tells you what the escape velocity is. If I put this equal to 0, and then just solve for V, you just find that V squared, escape velocity, little e here is escape velocity, is just given by 2 goes up from here to here, gm upon r. And where m is the mass of the earth, g is Newton's constant, and r is the radius of the earth up here. So the statement is that because initially, so the question is really what velocity I have to throw the ball up initially, and initially therefore the ball is on earth, so this is r, capital R, the radius of the earth up here, and therefore initially this equal to 0 tells me that the escape velocity should be equal to given by this equation where this little r is the radius of the earth, and therefore we get this step up here. Good. So therefore, if in fact the velocity actually exceeds the velocity of light, if the escape velocity of the ball exceeds the velocity of light, then that means that even light cannot escape, and light would also be trapped by the gravitational pull of Earth, or the mass m up here, and therefore we are going to have a black hole if in fact 2gm upon r is bigger than or equal to speed of light squared. Now I can translate this equation in terms of the density. Let's just suppose that the body that we're talking about, Earth in this case, or whatever the body may be, is really a sphere, and it's a sphere of radius capital R again, but of a uniform density, rho. Then I can convert this mass by the formula that m is equal to 4/3 pi r cube, that is a volume, times the density. And when I substitute this here, I just obtain the same equation, 2g, and for m, I'm just substituting the 4/3 pi r cube times rho, divided by r, but I got here r cube, the volume of the sphere, and therefore r cube divided by r gives me r squared. So we get this equation. And this equation is slightly easier to sort of work with than the previous equation, because it tells you immediately that there are two ways of making a black hole. What we can do is, speed of light is very, very large in your MKS units or CGS units that you use. So what you can do is to, and G is quite small. So what you have to do is to either increase R or increase rho. You can have an object which is very, very dense. So if I got very, very high density, so for example, if you can compress sun to a radius of 3 kilometers, then the density will be about 5 times 10 to the 18 grams per cubic centimeter. The density of a nucleus of a matter is about 10 to the 15 grams per cubic centimeter. So this is 3 orders of magnitude higher. Then in fact, this equality is satisfied, and this little Newtonian calculation will tell us that that there is actually a black hole, that the sun would become a black hole if it is compressed to a radius of 3 kilometers. Or what we can do is just keep this rho to be small, for example, density of water, 1 gram per cubic centimeter. And then you will have to have a huge R. How large R? You can just substitute and find out that the radius has to be about 10 to the 8, so 100 million kilometers. So if you build a water tank, just ordinary water tank, but a huge one, right, with 100 million kilometer radius, then you will have a black hole. And interestingly, both of these kinds of black holes exist in nature. And we're going to see how this happens. These are black holes which are kind of solar masses or tens of solar masses, and they have been seen through gravitational waves. We'll see this. And the really large black holes, because even though the density is very small, because the radius is so large, the mass of this black hole is about 1 million solar masses, and they occur in the center of the galaxy. So such ideas were discussed. As you can see, we just use Newtonian gravity. So of course, they were discussed soon after Newton published his Principia, or 230 years ago, long time ago. And this is a paper by John Mitchell in the Philosophical Transaction in 1784. And he said, if there should exist in nature any such bodies of this kind that we talk, then of course they will be black because light cannot escape. So we'll have no information from sight. Yet, if other luminous bodies like stars, for example, should happen to revolve around them, we might perhaps see them from the motions of these revolving bodies. Just as, for example, because of sun, the planets go around the sun, or because of Earth, the moon goes around the Earth. So even if you did not see the Earth, but if you just saw the orbit of the moon by Newtonian gravity, and equations, Newtonian mechanics equations, you will actually be able to conclude that there is a central body, which is Earth. And so they thought that maybe one can actually look at, even though you don't see the black hole, you can see its effect on other bodies that you can see, like stars, and therefore you can conclude that perhaps there is a black hole. And we will see that, in fact, the 2020 Nobel Prize, by half of it was given to Genzel and Gens, and this actually used exactly this idea. There's also, you might have heard about Laplace, like Laplace equations. So Marquis de Laplace, or Peter Simon Laplace, he wrote this treatise called Exposition of the System du Monde, expositions of the system of the universe, and there are 2 parts. And in that, he explicitly said that if a luminous body has the same density of Earth, but whose diameter is 250 times larger than that of the sun, then by its attraction, it can prevent light from reaching us. And consequently, the largest bodies in the universe would remain invisible to us. And there may exist in the immensity of space, opaque bodies of considerable magnitude. There may be lots of black holes. So these ideas are very old. They're just using Newtonian gravity. But in the next part now, I want to tell you why this explanation is conceptually incorrect and why we need general relativity. Are there any questions at this time?
No,
I don't see any
none as of
questions.
now.
Yeah. So let me go to the next part, which is general relativity. So this ordinary Newtonian gravity, I hope you understood this reasoning. But the reasoning behind these fascinating conclusions is in fact conceptually incorrect. In fact, in Newtonian gravity, there are no black holes. Why is it? Well, all speeds, as you know, in Newtonian gravity are relative. So for example, if you are driving in a car and you have got headlights on, then that light, the speed of that light, which is escaping the car, would be given by your velocity v plus the velocity of light. Everything is really relative. And similarly, with respect to you, it will be just the velocity c, but with respect to somebody sitting by the roadside, the velocity of light will be v plus c. So all the velocities are, including that of light, are. And so, therefore, it predicts that we should be able to see black holes by reflected light. You see, how do we see moon? The moon doesn't have any light of its own, but it reflects the light of sun. So what happens is that sunlight falls on the moon and then is reflected back to us. Now, in Newtonian theory, and in what I was talking about here, like, I started with tennis balls and so on, and then went on immediately to a small tennis ball up here, and then went on immediately the speed of light. And so here, what I'm doing is really using the idea that light is made up of particles. This was Newton's idea, corpuscular theory of light. And you don't know how much mass it is. They thought it was very, very small. But anyway, this equation doesn't depend on the mass. As you can see, mass just factors out. If I put this equal to 0, mass just goes away. So Supposing, in fact, we got these little particles, and these little particles, so here is, say, for example, somewhere here, maybe the candidate black hole, and I'm shining light towards it, right? And if I'm shining light towards it, then what would happen is, so here is the candidate black hole, and I'm shining light towards it. So I'm shining light towards it. Light is coming like that. Then it would, this is a bunch of particles. And just like the tennis ball, if you throw it on the earth, it will bounce back. So this light will bounce back. And then in this process, as you probably know, momentum is conserved. And therefore, what is happening in Newtonian description is that maybe light is emitted out here somewhere. And with respect to the source of light, maybe the speed of light is just c. But as it falls in the gravitational field of the body, which you don't see, which might be a black hole, so to say, which is a candidate black hole. So then what will happen is that these particles will accelerate. Therefore, their velocity was equal to c with respect to the source. But by the time they arrive at this black hole, the candidate black hole, that in Newton's gravity, Newton's theory of gravity and mechanics, the speed will be larger. And therefore, by conservation of momentum, it will come back again. And in fact, it will then, because its speed is larger than the speed of light, so to say, therefore it can actually come back and come out of here. So just by conservation of momentum, just as we see the moon, it should be possible to see also the black hole. We should also be able to see the black hole, not by the light it emits, but by the reflected light. So really, in Newtonian gravity, this description of light being trapped is really incorrect. If you are conceptually follow it through, there are no black holes in Newtonian physics. So for black holes, what you need is the following. You need both an absolute speed of light. So it doesn't really depend on whether it is with respect to the emitter or with respect to the absorber, the putative black hole. The velocity of light is completely universal. So this violates Newtonian idea that the velocities are all relative. And that is what is a fundamental building block of spatial relativity, that the velocity of light is absolute, doesn't depend on the motion of the observer. And of course, you also need gravity. So you need absolute speed of light and you need gravity. Absolute speed of light is what gives rise to spatial relativity. This is the absolute speed of light, the spatial relativity. But you have to add gravity to it. And when you add spatial relativity and gravity, you obtain what is called as a general relativity. And then the statement is that you need general relativity. Now, this diagram on the left-hand side is not something that you have to worry about too much at the moment. But basically, what can happen in general relativity, because I'm going to come back to that. But what happens in general relativity is that there can be, this is space, in this direction is space, and this direction is time. So this is called the space-time diagram. And therefore, an observer, for example, you are described by a line, because as the time ticks, you are at the same place. And therefore, you trace out a line. It's called a world line of the observer. And that what can happen is that because of some star or something which collapses, what can happen is that there can be regions in space-time which are such that in that region, light can be completely trapped. But we really need both gravity and absolute speed of light for black holes to exist. And that is why general relativity is essential. So general relativity is essential. And this, by the way, this picture is adapted from the Penrose's figure that the Nobel Committee used in its announcement of the prize. So what is general relativity? Well, general relativity, what happens is that gravity fuses with the space-time geometry. So this is a very bold idea. You see, if you look at normally, you think of space and time as being just given to you. They're just sitting there. They're not, nothing much is happening. They're just sitting, space and time are just sitting there. But that is in Newtonian gravity. But in general relativity, the idea is that there is no such thing as gravitational force, but rather in presence of heavy bodies like the sun here, which is at the bottom of this potential well that you see up here, the sun actually bends space-time. Bends, and therefore it is bending the space. You think of it as a rubber sheet, and little objects like Earth move in the geometry of this bent space-time. And therefore, with respect to a Newtonian observer, or Newtonian analyst, so somebody does analyzes it in Newtonian theory, would actually feel that the object is actually turning around and it is being attracted towards the center. But in fact, what is happening is that it is really following the simplest trajectory it can, the straightest trajectory it can, but in the curved geometry of space. And that is why in Newtonian theory, it will look like an elliptical orbit, but in fact, it is at any given instant, it is just reacting to the curvature of space at that point. So gravitational field is encoded in the very geometry of space-time. And this is possible because gravity is omnipresent. You cannot switch off gravity and you cannot switch off space-time. And therefore, the statement is that space-time is everywhere. Similarly, gravitational field force is everywhere. So why not identify the two and encode the gravitational force into the very geometry of space-time? And it is non-discriminating. That is to say, gravity acts the same on all objects. You know, you can have electric charge. Gravity doesn't care about that. It only cares about the mass, and mass always has the same sign. So electric force will act in one way. For example, if you have negative electric charge and you have some lines of force, the negative charge would move in the opposite direction of the lines of force, whereas the positive charge would move in the direction of the lines of force. So electromagnetic field force discriminates among particles. It can tell one particle or the other, whereas in a gravitational field, all particles fall the same way. So that is why we can encode the gravity into the geometry of space and time. And basically, Einstein's equation tells us the following. It tells us that matter, if you have matter, then space-time is bent. And Einstein's equation tells you how much bending there is, how much curvature there is for a given amount of matter. And then this bent space-time, this curved space-time, a bent space-time tells matter how to move. So that we just saw up here, that this planet is moving in this particular way in the gravitational field of the sun, is what Newton would say. Whereas Einstein would say that, no, the planet, the surface has bent space, and planet is moving as in the simplest possible trajectory, trying to go instantaneously as straight as it can. But because space itself is curved, then with respect to Newtonian perspective, it would look like the particle is actually going in an elliptic orbit. And the geometry, as I said already, is intertwined with matter via Einstein's equations. So this is the basic idea. Let me tell you a few things about general relativity, and then we'll go back to the questions. So Einstein published the general relativity in November of 2015, so 105 years ago. And actually just 2 days, 26th of November is when he sent the paper to the Prussian Academy. And then he wrote to Arnold Sommerfeld, who was the leading theoretical physicist in Germany at that time, in Munich. Einstein was in Berlin. And he said, during the last month, I experienced one of the most exciting and one of the most exacting times of my life. True enough, also one of the most successful. And then he explained that, well, not only you could encode the gravitational force in the curved nature of space-time, but when he did calculations, he resolved a puzzle associated with the orbit of Mercury, which had been with them for many decades. But it took non-scientific world events to intervene for general relativity to be accepted as a revolutionary shift in paradigm. It is really a revolutionary shift because for thousands of years, everybody thought of space and time as being just God-given, given like an arena or a stage on which things happen. They are not physical entities. They cannot be acted upon. They do not act back on you. Whereas Einstein completely changed his perspective. And it is because of this, as we will see, that we can have black holes in general relativity. So what are the world events? The world event was really observation of bending of light by gravitational field. So as we saw here, there's something like sun bends space around it. So if the light is traveling, it is going to go down and then come back again up here. And therefore, if I'm sitting up here, so light is going to go down and come back here. So if I'm sitting up here, I extrapolate, and if I don't know that space is bent, time is bent, I will think that the source of light is somewhere here. Whereas really it is here, and it is a bending that has really given me an apparent shift. So Einstein calculated, just 1 second, Einstein calculated this shift and found some value, and he found the value to be 2 times what happens in Newtonian gravity, and that is what was actually verified by Arthur Eddington through a solar eclipse mission up here. And this happened then in 1919, so November 1999, 4 years ago, 4 years after that. And then these were, Einstein instantaneously became a household name. There were all these headlines in New York Times: lights all askew in the heavens, men of science more or like agog, or results of eclipse, etc., etc. The reason is because Newton's theory had been around for more than, for more than 200 years, and everybody thought it was absolute, and Einstein completely changed that paradigm. And here is kind of the bending of life that actually can cause a gravitational lens up here. So as you can see, that even though the main ideas were laid down already in 1915, it took 4 years, not 5 years. 4 years. It took 4 years for the scientific and also non-scientific events. What happened is that this mission was actually carried out during World War I, and this really was a great symbol in which a German scientist had proved a theory which was verified by British scientists, and therefore that really sort of showed that science transcends all these petty considerations of human beings, and that really was the reason why Einstein became so famous and general relativity was accepted. So I just want to end with a side remark up here on general relativity, and then we'll take questions. So one can ask the question, okay, this is all very fancy and this is all very nice, that space and time are bent and all those things, but really who cares? All these things are going to be important only when gravitational fields are very small, are very strong, and the effects are going to be negligible on Earth, because the bending of light, as we saw up here, is a very small effect. Similarly, the perihelion of Mercury is a very, very small effect. So who cares? Now, I want to tell you something that you please remember, because then you can talk about this when you talk to your teachers or your mentors, or even your parents who tell you that you must do engineering and not physics and so on and so forth. The point is that fundamental laws of nature always matter. And why do I say that? Well, you all have cell phones. You all have cell phones. I don't know if you see my image, but I'm holding my cell phone up here. In the cell phone, there is a device by which you can it tells you where you are. You can, follow a map, for example, as where you are moving and so on. And all that happens because of the global positioning satellite system, GPS system. But GPS system needs general relativity, because the satellites are out there and they are in the curved geometry of Earth. And because of that, the time ticks there at a different rate than the time ticks on Earth. And if you ignore general relativity, then within 2 minutes, the GPS localization errors will grow to 23 meters. In other words, you will not be able to tell your position. The error bar on it will be about 23 meters. Now, you all know that airline pilots use GPS, use this automatically, and they have to land on a strip. And on a runway is about 10 meters across. And therefore, if less than 2 minutes, the pilots would not be able to land the planes on the runway if they ignore general relativity. So fundamental laws of physics always matter. And this is an example that GPS would not work without general relativity. Okay, so this is the second part that I've done. We've done these 2 parts, and now we're going to go to the history of black holes. But there are a few questions in the chat box, so let's take them.
So I'll read them out. There have been a few questions, so I'll read them out to you one by one. So
Yeah.
The first question: what does it really mean when one says that space-time is curved? Does it mean that the space-time is a geometrical entity? How can time be integrated into the familiar geometric space? And also, what makes the space-time fabric to hold such a massive entity?
Right. So the point, yeah, good. So first of all, the discovery of general relativity took place in 2 stages. The first was special relativity. And special relativity came about to resolve a conflict between Newtonian mechanics, laws of space, Newton's notion of space and time, that time is absolute and so on, and space is absolute, and the theory of electricity and magnetism. So around 1850, Maxwell, James Clerk Maxwell, a Scottish physicist, succeeded in combining all our knowledge about electricity and magnetism in just 4 equations. And those 4 equations are called Maxwell's equations. And their consequence, there are 2 very, very strong consequences. The first was that because of combining all the equations, he saw that electromagnetic waves actually are real and they can actually propagate in space. And secondly, he saw that the speed of this of electromagnetic waves is absolutely constant. It doesn't depend on anything, observer or anything like that. And that contradicted Newtonian mechanics, because in Newtonian mechanics, all speeds are relative. And the long story about how this was finally resolved, but the final resolution came in 1905 due to Einstein. And there he found that in fact, space and time in fact fuse into a 4-dimensional continuum. What does it mean? It means that normally you think that you know what are simultaneous events. Something happened at the same time at 2 different locations in space. But really, that is an approximation. That is something, an absolute simultaneity is an approximation if you don't look at events which are very widely separated with respect to each other, or observers moving at the speed.
We're sorry for that. We've removed that person.
Yeah. Okay. So the point is that Maxwell theory is actually going to tells you something that contradicts relativity, and Einstein was led to fuse space and time into a 4-dimensional space-time continuum. You see, physics or nature is really not so easy to comprehend to human mind, as we will see more and more. But that is really a reality. That is really a fact, that space and time are fused together, and our usual notion of simultaneity, absolute space of Newton or instant of time of Newton, for all observers is only an approximation. If observers are moving with respect to each other at large velocities, then the events which took place at the same time for one observer do not take place at the same time for another observer. For this reason, for example, in CERN, in the international accelerators, one actually sees that lifetime, the duration of time of an elementary particle depends on the rest frame. In its own rest frame, it has 1 lifetime. In our rest frame, the lifetime looks much larger. And these are all verified every day. So space and time really fuse into the space-time continuum. And your second question was, how is it possible? Well, it's a fact of nature, right? So this is what is happening. You might ask, how is it possible for sun out there to pull Earth and make Earth go around it? Well, the point is that it's there, and our job is to describe what happens. Next question, please.
Yes, sir. So this is regarding the first section. So is there a limit for the density rho beyond which we cannot increase it by? So is there like an upper bound on the density in your earlier section?
Right. In the known physics, not sure. Physics, which is very well established and tested in a lab and so on and so forth, we do not have a dense upper bound like that. But if you combine gravity with quantum mechanics, which is very forefront of physics, so in the work area that I work with, which is loop quantum gravity, that does tell you that there is an upper bound, absolute upper bound on the density, just like there is an upper bound on, on velocities. You cannot make a particle move if you start from rest in your lab. You cannot make it move with a velocity greater than the speed of light, because then you need infinite energy to do that. So similarly, there's an absolute bound on the energy density, and that is about 10 to the 94 grams per cubic centimeter. So it is really much larger than the numbers that we saw before. Next question, please.
Okay. And one final question before. So am I right if I say that the planet moves around a geodesic space-time membrane? Are these the right words to use?
I think you should just say it moves in geodesic in space-time. Just drop the word membrane. It's a four-dimensional continuum. A membrane usually means some object which has lower dimensions than four. So this is geodesic, which is moving in four-dimensional curved space-time.
Okay, thank you, sir. I think we'll take the other questions towards the end. That's more
You
sort of a general in nature. So
okay. So now let me start with this third part, which is really about the black hole up here, the curious history of black holes in general relativity. So the simplest black hole solution was discovered already during the First World War, just 4 years after Einstein discovered general relativity, by Karl Schwarzschild. But its clear interpretation of the black hole had to wait several decades because the leading researchers really did not understand the interplay between geometry and physics very well. And that was really a problem up here. Now, initially, there was a great deal of confusion about what we today call event horizon, which I'll explain in a second. The three-dimensional surface, hypersurface, in space and time given by the constant value of r, the value that came out of that escape velocity formula, r is equal to 2gm upon rc squared. So here's the picture. As I told you before, the same picture as before, drawn by Roger Penrose. So up here is time, and these are three space directions, which are just combined, x, y, z, just combined up here in three dimensions up here. And therefore, as I said, this is an observer, which is a world line, and here is a star. So this star is depicted here by, it's a three-dimensional object, but depicted here by 2 dimensions because I don't have a good enough way of drawing it. And supposing the star collapses, so its radius is increasing as you go, decreasing as you go along up here. So what happens is the following. Out here, these are the trajectories of light rays. So if you like this, they form a cone, and as you can see, the cone out here is kind of vertical, it's straight. But as you come closer and closer to this region where there's matter and space-time is bent more and more, it's curved more and more, then this light cone starts tipping in this direction, as you can see up here. And therefore a stage comes in which light cones have bent so much that all the tipping has happened so that all the light rays are going to be trapped in this region. They cannot really escape this region at all. If you go further in, then they're even more tipped, and the light rays are then really trapped in this region. They cannot go out of this region at all. And every time they will just be but circulate in this region. It will not nothing will happen. And that is the reason why. So this is supposed to be a spherical star which is collapsing and giving rise to this dark region. And now this dark region is dark with respect to any observer. If I were to shine light here, as I was doing, like a moon, if I were to shine light will come in space-time. It is coming up here. It is moving in time as well as space. So it is going to go like that in light, space, and time. And therefore, it comes like that in Newtonian gravity. Because of conservation of momentum, it will be reflected out. Whereas here, the point is that it cannot reflect out. Once it gets inside, it really is trapped. It's trapped because speed of light is just constant. It's not. So the speed of light was c here, and even if when it come here, it is just c. It is not increased. And this region, for all observers, the light is trapped. So it really becomes an observer independent statement because of 2 reasons: speed of light is absolute, and space-time is bent so much. So the whole question was that the Schwarzschild solution was interpreted as an external solution of a star. So if you have a star up here, then outside the star, the solution will be described by Schwarzschild solution. But then when it came to this r equal to 2gm upon c squared surface, people thought the solution becomes infinite, becomes singular. There are infinities in the solution. So people thought that means that I cannot really talk about that surface. But actually, pioneering works of Lemaitre and Finkelstein showed that these infinities are just fictitious, and physically, nothing happens around the surface. It's a perfectly fine surface. What is happening is that inside it, light is just trapped. But there's a curious history of these black holes. The question is whether black holes exist in nature. First of all, one wanted to understand that black holes are admitted by general relativity. And secondly, even if they're admitted, are they just mathematical entities or do they exist in nature? And our own Professor Chandrasekhar, I was very happy to be in his group in Chicago. He discovered, and this is really very, should make you feel thrilled and give you goosebumps. He discovered it. Chandra was born in 1910. So he discovered it starting from age of 21 to 25. And 21 is when he first discovered it, and then he refined the arguments over time. So basically, he showed that, in fact, if you have heavy stars, like our sun, for example, we can ask, why is it that the sun doesn't collapse at the gravity? Because everything is pulling it towards the center, right? There are gases, and why doesn't it collapse? Well, it's because of nuclear reactions inside the sun. Because of nuclear reactions, heat or photons are emitted, and photon produce some pressure. And that pressure balances the gravitational attraction, and therefore the sun does not collapse on itself. But what happens if, in fact, the star runs out of nuclear fuel? It burns all its nuclear fuel. And Chandra realized that if you did that, that during the boat trip to England, when he went to Cambridge at the age of 20 to do his PhD, he realized that, in fact, the star would become what we today call black hole. And then in 1939, Oppenheimer and Schneider considered spherically symmetric gravitational collapse and showed that there was actually a black hole also. By the way, sometimes in the Indian press, people have said that, in fact, in 1937, there was a paper by Professor Dutt, which actually anticipated this Oppenheimer-Schneider collapse. I read that paper in great detail, and I think this conclusion is just incorrect. There is no mention of black holes, so there's no mention of trapping up light. There is no such mention. There's no mention of matching the interior region of the star with the exterior region of the star, etc. in this work. So I really think that Oppenheimer Schneider were the first people to show in general relativity that black holes can form. But the problem was that the problem was the following: that even though there are these calculations show that black holes should be formed, there was a general reluctance in accepting the idea that stars more massive than Chandrasekhar limit will have no equilibrium configuration once they exhaust their nuclear fuel. Astronomers, by and large, preferred a serene, calm universe. For hundreds of years, they thought the universe on a large scale was serene and calm. There are fixed stars and nothing happens out there. Imperfections are all nearby. Far away, the universe is serene and calm, not a violent one. And there's also a quirk of history. The day that this paper appeared in Physical Review, in fact, Hitler, the day that this appeared, Bohr and Wheeler published a paper on nuclear fission, and that was really very important politically and so on and so forth. And also, that was also the day when Hitler invaded Poland. And so all these things happened together, and then this paper was actually ignored. But the real reason was that astronomers preferred a serene and calm universe and not a violent one. The reluctance to accepting the existence of black holes, both Einstein and Eddington, even though they were pioneers of general relativity, opposed the idea of black holes. Eddington sort of put down Chandrasekhar at many times, but Chandrasekhar, being Chandrasekhar, actually kept his friendship with Eddington until Eddington passed away. And Eddington said something like, various accidents may intervene to save the star, but I want more protection than that. I think there should be a law of nature to prevent the star from behaving in this absurd way. That absurd way refers to what Chandrasekhar had found. Now, these arguments that Eddington gave, if they were given today by a PhD student, the PhD student will fail in his comprehensive exam. So they are completely wrong, but nonetheless, these people were so prominent that the ideas were resisted. Einstein himself published a mathematical paper. It was not like the Eddington thing about what I want. It was a mathematical paper. And mathematically, he showed, and the paper is correct, that you cannot form a black hole through gravitational collapse. Even though Oppenheimer-Schneider just a few months later showed that this was in fact possible. And the reason is because Einstein was trying to use an approximation that the collapse should be quasi-static. It should happen very slowly. Whereas in fact, the collapse happens in a millisecond. The whole solar mass star collapses in a thousandth of a second. And therefore that approximation was wrong. So it's really the reason why this Nobel Prize was given to Penrose was because in 1965, Penrose's paper showed, and without any symmetry assumptions, because people also thought that maybe Oppenheimer is right, but in fact, Oppenheimer assumed that the star was exactly spherical, and as soon as there are spherical, no star is exactly spherical. As soon as you have a little bit of deviation from spherical symmetry, there would actually be no singularity, and therefore no black hole, and this collapse would not happen. The endpoint would not be a black hole, and various influential Soviet school was actually pushing in this direction, led by Lifshitz of Landau Lifshitz and Kalatnikov. But in 1965, Roger Penrose showed a general paper, very, very general, beautiful paper, and this is what was quoted in the Nobel Prize announcement, without any symmetry assumptions, that if one accepts general relativity and physically available matter, then gravitational collapse is inevitable and leads to a space-time singularity, and therefore this this Oppenheimer-Schneider solution and what Chandra was saying is all really what happens in nature, and black holes should form copiously in nature. And that is what led to the Nobel Prize announcement on 6th of October, just about a month ago in 2020. So are there any questions at this stage?
Yes, so there's just one question. So before that, I must say that was like a really interesting section. Yeah, so coming to the question, so there's one comment which says space-time is like a grid of time and space. Space is the first three dimensions and time is considered to be the fourth dimension. Gravity is the curvature of space-time onto another direction, if I can call it so. Would that direction, can I call it the fifth dimension? Would it be right to call it, or is it directly responsible in some sense for the fifth dimension if something like that exists?
No, so there is no fifth dimension. So let me just it's just because of the way that we are, our intuition works. We think of curved spaces as being needing another dimension to live in. That is because we can only conceive a flat space. That is just our limitation. So for example, if I take a tennis ball, we think of it as being living in three dimension. So there's a two-dimensional curved surface which lives in three-dimensional flat space. But it's ours kind of intuitive and desire to put this in a higher dimensional space. The tennis ball the surface of the tennis ball can be understood by itself without referring to a three-dimensional space at all. And one can calculate and show that it has a curvature. So similarly, space-time is a four-dimensional continuum, which is just curved. So it really is inside space-time itself, one feels this curvature. Now, if you wanted to just invent a fictitious higher dimensional space and embed this space-time manifold into that higher dimensional flat space, mathematically you can do that. But there's no unique way of doing it. And in general relativity, the whole idea is that there's no need to do it. As a mathematical simplicity, you might want to do that, just like we think of the tennis ball as living in three-dimensional space, because we are so used to three-dimensional space. But I can think of the surface of the tennis ball in its own right. It's a two-dimensional sphere, two sphere. Similarly, I can have three sphere, four sphere, etc. So I can have these curved surfaces in higher dimensions without needing additional dimensions in which this curved manifold or this curved object actually lives. So space-time is a curved four-dimensional continuum in its own right without needing a fifth dimension.
Oh, thank you, sir. I guess I'll post there are like two other questions which are a bit more general. I'll post them towards the end.
Okay. So here is a Nobel Prize announcement that came in the 6th of October 2020. And it says it is for theoretical foundation. It says it's for theoretical foundation for black holes. And that is what I just mentioned, I explained to you. That is Penrose's work, theoretical foundation for black hole, that in general relativity and without assuming any symmetry, that they're inevitable if some conditions hold. And Chandrasekhar's work shows that such conditions will hold. And the other half, so half was given to Roger Penrose for theoretical work in 1965, and the other half was given jointly to Reinhard Genzel, and Andrea Ghez for the discovery of a supermassive object at the center of our galaxy. So let me start with the second part, which is the first part I already explained a little bit. So let me start with the second part, which is the supermassive object in our center of a galaxy. So on the left-hand side up here is a picture of our center of our galaxy. This up here is about 1 light year. So the amount of distance that is covered by light in 1 year. And right in the center of a black hole here, as a galaxy, center of the galaxy here, where you see these 2 arrows, is a small compact region. And that is where there is a black hole of about 4.3 million solar masses that is existing, 4.3 million solar masses. So it's one of those large black holes that I talked about, where if you quote unquote, if you want to think in terms of density, the density can be low, but the radius is very large. The radius is about 1 million kilometers, or 4 million, about 1 million kilometers. And the point is that now, how do you see this black hole? So for this, I just want to go back to the very first part of the talk and make connection with that part, that we saw that already John Mitchell said that if there should exist in nature any such bodies, we could have no information from sight. Yet, if other luminous bodies should appear to revolve around them, then we might perhaps, from the motion of these other bodies, infer the existence of the central one. And that is exactly what was done by the very, very careful, astute observations, which required completely new kinds of instruments to be able to look at the center of the galaxy and to remove all the other sources of noise there and so on. And they find many, many stars here. The Nobel Prize announcement singled out one. That small star is called S2 because it happened to be the second star that was second star that was actually discovered around the central black holes up here. So here is a central black hole, and here is the orbit of the star, as you can see. And they observed it carefully from 1992 to 2018. So, it's 22 years or so, 28 years or so. 26 years or so. They observed it very carefully up here, and they found that in fact the star is going around exactly as though there is some heavy body in the middle. There are many other stars, but this is the one which is sort of looked at very, very carefully, and they've looked at various characteristics of the star and so on and so forth. The characteristics of got details of the gravitational field of this central object. And they concluded that there is a black hole of this particular mass, or there's a compact object of this particular mass, and we don't know of any other compact object that can exist other than a black hole of that side. But there are also smaller black holes, and they're just of a few solar masses. So again, in the very beginning, I told you that there can be very large black holes with quote unquote low density. That was just an intuitive picture. Don't take density as being very serious, very obvious, very literally. But basically, that gave you intuition. And so similarly here, there are very large objects, and it is now believed that in center of almost every galaxy, there is a huge black hole like that between 1 million and 1 billion solar masses. But there are also smaller black holes like a solar mass or 10 solar masses or up to 100 solar masses. And they were observed in 2 different ways. Here is indirect observation, and in the sense that what one sees is that there is a central object up here, and there is a companion star, and this object has such strong gravity that it is sucking in matter from the companion star, and as it falls in, it makes what is called an accretion disk, and then it emits huge amount of light which goes up here, and this in a funnel-shaped way, like that, and these are actually observed, and therefore people have concluded they did not have such a detailed observation like the star going around and so on and so forth, but they concluded that there must be some very small compact object nearby. So this was not such a strong argument for the existence of a black hole, and that is why people took that to be an argument that there's a compact object, but it was not a kind of a clear silver bullet or clear indication of a black hole. But the clear indication of a black hole came from gravitational wave detectors. These have been operational for some time now, but since 1915, so for 5 years, they have been observing gravitational waves which are emitted by collisions of black holes, by mergers of black holes. And this is called a mass in the stellar graveyard. In other words, the stars collapse to make black holes, and then the black holes themselves actually merge. And these two objects merge to give you this object, these two objects merge to give you this object, etc., etc. And there are many events now. I mean, and in the so-called LIGO, which is Laser Interferometric Gravitational Wave Observatory, which is in the United States. There are 2 detectors and 1 Virgo in Europe. And from the first 2 runs, they observed this, and from the 3rd run, which is going on, they already observed something, close to 40 black holes up here. And these are really clean proof of black holes, because the way the signal has the signal that the gravitational wave detector comes really matches the predictions of general relativity, in which you take a solution of Einstein's equation in which 2 black holes collide or they merge, and you work out what the gravitational wave should be, and they match in complete detail. And that is why this is really clear proof that black holes do exist in nature. And now black holes routinely are invoked as engines driving the most energetic explosions of the universe. So this is the same image as this kind of image in which black hole is accreting matter and then emitting X-rays that can be seen. Here is actually 2 galaxies which are actually going to be merging. Our own galaxy is going to merge with Virgo. We still have a long time, but when it merges, the black holes in the center of those galaxies will actually merge. And here is a gamma ray burst, which in a few blinding seconds, more energy is emitted than 1,000 suns do in their entire lifetime. And these are occurring, every few hours in the universe, and one sees them, and the engine which can drive such huge bursts of energy is a central black hole also. So black holes are really ubiquitous. So I presented a paradigm shift in fundamental physics and astronomy. The first paradigm shift came from general relativity, the merging or fusing of space and time into a space-time continuum, which is bent. And once it is bent, the notion of black holes comes to forefront. And then there is a great resistance for a long time to the accepting that, first of all, black holes existed even as theoretical entities, and secondly, black holes existed in our actual universe. But the work of all these great people has really shown that they do exist. By the way, just the difficulty of this work is really is encoded in this following fact. In this Nobel Prize, it was given for the paper of Roger Penrose, which was given in 1965, right? And now the prize was given only in 2020. So it's, it took 30 plus 55 years for the Nobel Prize to be actually given. And the interesting thing is that 1965 is also the year that Andrea Ghez, the observer, was actually born. So you see, theory has run so much ahead of technology that it's taking more and more time to really verify the fundamental predictions. I mean, applications you can verify, but fundamental paradigm shift takes a long time to verify. And that is an example up here that we see. And here is a quote from a very famous biologist, Edward Wilson. He said, "The physicists succeeded magnificently, but in doing so revealed the limitation of intuition." And this is what I was referring to in answer to the last question about, 4-dimensional continuum, which is bent. So is there a 5th dimension in which this is living? This is because our human intuition is very, very limited up here. The bent continuum exists in its own right without having to embed it in another higher dimension. So Wilson said that unaided by mathematics and understanding of nature, physicists discovered, comes hard. The cost of scientific advance is a humbling recognition that reality is not construed to be easily grasped by human mind. So that's why you need these leaps of imagination, astute mathematics, very critical thinking of evaluation of your own results, and so on. But these paradigm shifts that have occurred, which are so spectacular and are verified observationally, they exhibit the sheer audacity of the human race to see what is way beyond what we directly perceive. And that is where the frontier of fundamental science today lies. Okay, that's the last transparency. Thank you.
Thank you very much. So this was indeed an incredibly mind-blowing session. So once again, a huge thanks to you. So we now open up for questions. So please use the chat box and do not unmute yourself. So by the meantime, you can post your questions in the chat box. Sir, so one question. So the Nobel Committee says discovery of supermassive compact objects. They did not use the word supermassive black hole. Is there any specific reason for that?
Very good question. Yes, there is a specific reason. First of all, the point was that, everybody thinks that Nobel Prize are complicated things, right? I mean, because it's not some linear recognition of one's work. And as we saw, general relativity became well known and well accepted, not because it was published, but because of the solar eclipse, which took place just after the war, which brought together Germans and British scientists together. And there are all kinds of things that happen like that, right? So with black holes, there has been a kind of a very cautious, Nobel Prize Committee has been very cautious. But as I just mentioned, that the real proof of black holes really came from this already in 1915. And the Nobel Prize was given for discovery of these black holes, or for the discovery of gravitational waves, and also the by implication, the discovery of all these black holes. It was already given in 2 years ago, 2017, I think. The Nobel Committee already gave a prize there. So in some sense, on the other hand, these discoveries that we have seen, like these discoveries, they are really spectacular in terms of technological advances, in terms of observations, the infrared technology they had to develop, astute observations they had to do for so many years, right? 1992 to 1918, for so many years, they had to do this observation very carefully. So they wanted to recognize this as well. But this is not kind of a, silver bullet of a black hole. I mean, there's no other candidate that we know that would actually would actually be responsible for 4.3 million solar masses in such a small volume of space. But we are not. I mean, what we have done is really verified the low order general relativity here by looking at the orbits of the planets which go around here. We are not really verified in this. We had this discovery that it's a kind of a clear proof, silver bullet, which actually tells you that this is a black hole. And that is why they call it compact object. The real silver bullet or real clean proofs really come from these gravitational waves detections, which really agree in great detail. The signals that you see completely match with the predictions of general relativity. I mean, to get these predictions out, you need computers, you need numerical simulations, literally tens of thousands of hours of work by hundreds of people were needed to prepare these tablets, these templates for the waveforms that come out of general relativity, and they were actually seen in this thing. So this really is a proof of black holes. The other one, that's the reason why Nobel Prize the committee did not want to label it a black hole, but label it just as a compact object. It's a very nice question.
Thank you, sir. So one more question, maybe on similar lines. So why do we so strongly believe that there is a supermassive black hole at the center of every galaxy? Is it just because almost each galaxy we have observed has that at its center, and thus it is a natural to postulate that all of them have it? Or is there some pattern that has been found that requires their existence theoretically?
Yeah, so many of these galaxies, for example, have jets like that. And we don't know any mechanism that would actually produce so much energy, right? I mean, as I was saying, in a few blinding seconds, it's more energy emitted than 1,000 suns. And so that's one reason. And the second reason is really that it's a consistency argument more than anything else, namely that, there are observations which shows that there are some compact objects in the center of the galaxies which are responsible for holding the matter together, so to say. But I think it's also a theoretical consistency relation, namely that if you assume that there is this black hole in the center of galaxy, then you can theoretically work out what the dynamics of galaxy should be like. And galactic dynamic actually is very well modeled by this hypothesis. So it really is coming together of all very, very different pieces. It's this idea about, well, what is the simplest explanation? And looking at the fact, if in fact one assumption is able to account for numerous explanations, then numerous observed phenomena, then you believe in it more and more. So many facts about galactic dynamics and about energetics, about events like that, are actually something that can be explained by there being a black hole in the center of the galaxy.
Thank you, sir. And yet another question. So this is regarding your earlier sections. Why is the Chandrasekhar limit a certain value of solar masses? Is that just does it just happen that where the inward and outward forces manage to just balance each other, or is there something more to that at play?
Yeah, so that's a good question. Since people are asking such questions, allow me to be just slightly more technical. Okay, not very much. But also, Chandra is one of us, right? And so we should. But by the way, I'm not being disrespectful in calling him Chandra. He is himself wanted us to call him Chandra when I was a student, and then I was the good fortune to become quite a good friend with him in later years. So Chandra, in this boat, I mean, it's a fascinating story. So please allow me for 3 minutes to just tell you this story, but because I hope that it will really inspire you.
Absolutely, sir.
So Chandra was a student, undergraduate student, BSc student in the Presidency College in Madras, and there he was also the head of the the physics whatever, the physics committee, physics club, and they actually, it's totally unbelievable. We're talking about 1920s, right? I mean, so they managed to get Heisenberg, when he was visiting to India, they managed to get him to come and give a talk. And they also managed to get equal luminaries to come and give them talks right there. And there Chandra picked up that this idea of a special relativity and how kinetic theory of, how thermodynamics or how kinetic theory of gases and so on would be actually modified by special relativity. Now, until then, people were always using statistical mechanics, if you like, which is all kind of Newtonian mechanics. They're using Newtonian mechanics to talk about statistical mechanics. So Chandra realized that we could actually we should use special relativity. I want to emphasize, Chandra did not use general relativity. He used special relativity only. And then he found that in this famous boat trip, I mean, the paper appeared in 1931, but really things were worked out in the 1930. He is a 20-year-old kid, right? I mean, so it takes a while for radical ideas to be accepted by the scientific establishment to be published. So what he found was the following. So he had this idea that maybe stars actually burn their nuclear fuel, and then when they burn their nuclear fuel, what will hold them together? So the question was right on target. The question is what will hold them together? And the idea here was that what will hold them together is what is called Fermi degeneracy pressure. So you see, if you got two spin 1/2 particles or half integer spin particles, like neutrons or electrons, then the statement is that you cannot say neutrons, and so we can forget about the electric force. Then the idea is here that these two neutrons really cannot occupy the same state. This is what the Pauli exclusion principle tells us. That means that if you have a collection of such neutrons, then there will be some repulsive force between them. And so Chandra realized that, in fact, well, what will hold stars after the nuclear fuel is burnt out is really this balance between, as the question was asked exactly, was the balance between the repulsive force of this Fermi degeneracy pressure, as it is called, and the attractive force of gravity. And now the point is that the Fermi region, so the question was of actually finding out the Fermi degeneracy pressure, and the calculations up to that time were all done in using Newtonian statistical mechanics. And so Chandra introduced their special relativistic statistical mechanics. And by introducing this, by the way, this is something also he learned completely on his own from books by Sommerfeld that I mentioned to you, that Einstein had written to Sommerfeld before. And he found that, in fact, this was that, in fact, if the mass was bigger than 1.4 solar masses, then the Fermi degeneracy pressure would not be enough to support the star. And therefore, the star would have to keep, gravity would win, and the star would actually keep collapsing. So if there's a more massive star, then the statement is that there would be gravitational collapse. Okay.
Thank you, sir. And just one more question. So, can you explain in layman terms what the Penrose process is?
Yeah. So if you have a black hole, and let's see, I think the best thing is to sorry, I just let's see, how do I get a new one? Just 1 second. Maybe if I can't get it, then I'll just stop.
The plus on the top left of your screen.
Thank you. Yeah. Now the subject divider, right? It's not a new one. It's not place.
Sorry, the pencil mark, I think so, on the top right.
Right. Thank you. So the basic Chandrasekhar process is the following: that supposing you got the Penrose process is the following. Supposing you got a black hole, and if it is rotating, okay. So here is I'm just drawing it in space now. So if it's rotating, then oops, this is wrong. I should hold it. Yeah, this black hole is rotating, is going around this axis up here. Then what happens is the following, that even outside the horizon is a trapped region. So there will be a trapped region up here, and this will be just black. But what happens is that there is a region outside the horizon from which signals can escape to infinity. So light rays from here can escape out to infinity. They can go out. Whereas in this region, it's completely black. So in this region, the light rays just remain in this region. They cannot go out to infinity. They're just trapped up here. So this is the black hole region. But outside the black hole region, there is still a region in which light rays can escape. And the statement is that, yeah, this is a bad, yeah. Light rays can escape to infinity. And the statement is that, however, in this region, this is called ergo region, a little region outside the black hole. This is called ergo region. So all this region up here in blue is the ergo region going around. In this region, you can have particles with negative energy. Whereas outside this ergo region, energy of every particle is only positive. And so what can happen is that you could have a particle which is coming in, from outside. And supposing this particle comes in from a radioactive particle, and it decays into two particles, and one of them is actually trapped in this ergo region, remains in this ergo region, and the other goes out to infinity. Then in this region, you can arrange kinematics such that the incoming, outgoing velocities and so on and so forth, that such that in this region, this particle has negative energy. But of course, the particle which came in, this particle which came in, it was outside, so it had positive energy. Let's call it E. So this particle which stays inside up here is, so let me draw another this particle which is trapped, which remains inside, is brown now, and supposing its energy is minus, it's negative, so it's minus delta, say. Therefore, the energy of this particle which goes out is going to be equal to E plus delta, because I got total energy is E minus delta state is captured, and E plus delta. So what you are succeeded in doing is really creating a shell, or creating a bunch of negative energy particles which are orbiting around the black hole up here, trapped in this region. And in doing so, you actually get more energy. So you can extract energy out of the black hole. What you are extracting is the kinetic energy. So you're slowing down the black hole slowly, because this you can show that for this to happen, the brown particle has to be counter-rotating with respect to black hole. So its angular momentum is going to be reduced, and therefore the black hole is going to be slowing down. And this process will continue until the angular momentum is completely gone, and it becomes a spherical black hole, becomes a Schwarzschild black hole, and then you cannot continue anymore. But until then, you can extract this energy. So this is the layman's picture, and I hope that helps.
Thank you, sir. And yet another question. So has there been any experimental verification of Hawking radiation? If yes, will we be able to locate and identify black holes from their Hawking radiations?
Well, the thing is that for macroscopic black holes, for large black holes, even solar mass black hole, the Hawking radiation is extremely feeble. It corresponds to temperature, like black body temperature, about which will just not be observable at all, to 10 to the minus 8 degrees or so. So it is much smaller than even the black body temperature. So the direct observation of Hawking radiation is not likely to be possible. What people have done is to construct analog systems in the lab, in which one can see the analogs of Hawking radiation. But as usual, when you make some analog systems, the question is always about a little bit ambiguous about what is due to the accidental features of that analog, the atoms and molecules and so on that are there, that are not really in the real black hole, etc., etc. So there are analogs experiment, but not no direct observation of a genuine black hole evaporating. So there are further questions, so shall I go on, or are you still there?
So just a few other questions. We'll probably mail you the others. There have been questions flowing in. So if
I can see them, so I can just sort of answer a few of them, so that you don't have to. So
hello, sir.
Yeah.
Good evening, sir. So thank you for your wonderful talk. So I have a few questions. One question is.
No, please. I will not answer any questions that are asked directly. Just put them in the chat box, and then I'll answer them.
Oh.
And please switch off your mic, because we are hearing dogs barking.
Sorry, sir.
Yeah. So one says that, can you please explain the Penrose what Penrose published about black holes in 1965 journal? Well, what it showed was that it's a very short paper, but essential paper. It was what is called as singularity theorems. What it showed was that, in fact, under conditions that are, what I had said before, that if the matter in the universe is normal matter, so its energy is positive and so on and so forth, satisfies positive energy conditions and so on, then if this matter is sufficiently compressed, then what happens is that the geometry of space and time around it is bent sufficiently that there is what is called as a trapped surface forms. In other words, kind of instantaneously, light is trapped. But then he showed that if this happens, then space-time cannot be complete. There must be a singularity. And then that singularity is a black hole singularity. Another question is, can two black holes collide? If yes, what happens? Yes, black holes collide. And as I told you, that almost all the signals that were seen in the LIGO events, and there have been now close to 50 events, that in those, almost all of them, it is really two black holes which collide, and they form a single black hole which is larger. There are constraints on how much, how large. If you give me two black holes, then how large can the final black hole be? And from those constraints, you can see that in fact, in this process, energy will be lost, and these are the gravitational waves. Gravitational waves are ripples in the curvature of space and time, and they propagate from the event where the merger took place to where we are. Now, near the merger, there is a veritable tsunami. I mean, the space-time is just fluctuating wildly. I mean, you would not want to be anywhere near there. It's very, very, very much like a tsunami in the geometry of space and time. And then, however, as they propagate further and further out, this subsides. And by the time they arrive on Earth, the intensity, the amplitude of these waves is quite small, and that is why we need phenomenally accurate instruments, detectors, to actually see them. And these are obtained using, these detectors are the ones which employ lasers, these laser beams which go on 4 kilometers, and then it's really a technological marvel. Literally, the accuracy of this laser beam is that, just to give you some feeling, I mean, that if you wanted to measure the distance to the closest star, then you, in terms of accuracy, the accuracy of laser beam, this sensitivity of this experiment is to measure the distance to the next star up to the error being less than a human hair, the distance accuracy being. So it's really phenomenal. Or if you like, the displacements in the mirror that they see, if you deduce it, it would be like smaller than the radius of a proton. Of course, they're not actually measuring the radius of the proton. These are indirect things, but the accuracy is just phenomenal, and that is what is really needed. Okay.
Sir, I've posted a couple of questions which I've got in private chat, so it'll be there like towards the end of the chat stream.
Okay. Couple of questions I got. Okay, how does he? Yeah, so the basic lesson of general relativity that we. So the question is how do we quantize space-time, and does it? Can you find the theory of gravity in the very high energy scale? What, according to me, may be the other fruitful outcomes of general theory of relativity? So these are very different questions. So the first question is about quantum space-time. So as we just saw, that in general relativity, the gravitational force is encoded, or gravitational interaction is encoded in the very geometry of space-time. And therefore, the basic premise of loop quantum gravity that I work on is that means that the geometry of quantum gravity should be also a quantum theory of geometry. So we think of geometry as being a continuum. Even Einstein thought of it as a continuum, or general relativity with this continuum. But the idea is that it's a physical entity, Einstein told us, and matter is also a physical entity. The little screen in front of you looks like a continuum, but it's made up of atoms. It's just that the atoms are so densely packed that it looks like a two-dimensional continuum. And the idea up here is that similarly, space-time geometry really has some discrete structures, but it's those, if you like, fibers of geometry, the quanta of geometry, they're sort of knit together so tightly that we can approximate it under ordinary conditions by a continuum picture. But this is something that you have to show in detail mathematically. And then also you say that, well, if this is the case, when can we see the atomic structure? Well, as you can imagine, you can see this atomic structure. It comes on its own only in extreme circumstances near so-called space-time singularities, the Big Bang and the black holes. And so a lot of work that has happened is to show that, in fact, the Big Bang is not, there's no real singularity. It is really replaced by a big bounce. And that is because Einstein's equation received quantum corrections. And this is in reference to this high energy. Yes, there are quantum corrections. That is why we got highest maximum finite density, finite curvature. In Einstein's theory, curvature can be infinite. Here it is finite curvature, large but finite curvature. And that is why space-time singularities are kind of resolved, they're removed. And if you like, the quantum space-time is much larger than what Einstein taught us. Yes, so the question is there something called white hole which repels everything that we throw into it? It's not only repels, but in fact, things just like in black hole, things can fall into it, but things cannot escape from it. In classical general relativity, a black hole solution, white hole solutions are possible in which things can only come out of it. Things cannot fall into it at all. Such solutions, mathematical solutions, do exist, but this is an example in which one believes that in classical general relativity, in the classical world, if you forget about quantum effects, then these solutions are not really realized in nature. If white holes in classical general relativity existed, then that would mean that there will be no predictability because things can come out of the white holes at random, and we would therefore not be able to predict anything. So the general strong belief is that in classical general relativity, in the classical world, if you like, so long as the classical approximation holds good, then there are no white holes. The other question is, what, according to me, would be the other fruitful outcomes of general theory of relativity? Well, the three most spectacular predictions of classical general relativity are gravitational waves, which have now been finally seen, and we're learning through gravitational waves facts about a universe that we had no idea about before. It's really enriching our life, and that actually is one of the most dynamic areas of theoretical physics and astronomy today. We're learning, like, the rate at which we're making progress is really enormous there. The second big prediction was black holes that we talked about. And again, we're not at the end of black holes because there are all kinds of open questions about the kinds of black holes we see, how are they produced. It is not so obvious. Their production mechanism will teach us a lot about the environment that exists in the universe at large. It will also tell us about whether black holes were produced very, very early on by some unexpected processes, and so on and so forth. And finally, there is a Big Bang. And here, we're learning enormously about the large-scale structure of the universe by looking at the predictions of general relativity, the very early part. To me, it is totally spectacular that by looking at, basically, for example, if you were to use the cosmic microwave background, that looking at the tiny inhomogeneities, tiny anisotropies in the microwave background, which are 1 part in 10,000, we can actually predict the large-scale structure of the universe that we see today. To me, it is a phenomenal achievement of physics of the last 20, 30 years. Because cosmic microwave background came about when the universe was about 430,000 years young. And now we are about 14 billion years old. And so if you take the ratio, it is about 1 day to 100 years. So basically looking at the cosmic microwave background is looking at a baby when the baby was 1 day old. And of general relativity and astrophysics, all the things that we know so well as to predict what the baby would look like once you show the picture of the birth, and that it actually predicts what the baby would look like 100 years later. So imagine how much one would have to know about biology, physiology, biochemistry, molecular biology, and so on and so forth to be able to do that. And it's amazing that we can do that for the universe. So to me, these are the spectacular achievements of general relativity, and further progress is going to come from further deepening our understanding of the universe through these 3 channels. Maybe it's time to quit because it's now 1 hour and 30 minutes already.
Sure. So once again, thank you very much for this wonderful and this was incredibly extremely motivating session. So thank you for that. And so I'm sure like Professor Ashtekar has left many of you curious and your head is just bundled up with questions. So feel free to write out to us and we will compile all the questions together and get it answered as soon as possible. So
Okay,
I'm giving.
let me just say one thing that
Sure, sir.
our institute, which is called Institute for Gravitational Cosmos, or IGC, it's at Penn State. And you can just Google this, IGC or Institute for Gravitational Cosmos at Penn State, and we have an outreach page. An outreach page has a lot of semi-popular articles and YouTube videos, particularly, which are not random YouTube videos. They are very, very well thought out, well-made YouTube videos. So that would be very useful for younger people in the audience.
Thank you, sir. We'll definitely share across the link to the students as well. So, so as always, so as I said, so I'm sure all of you have many questions lined up in your head about this wonderful object of black holes. So do feel free to write out to us and we'll get them answered. So I'm putting out the ways you can reach out to us. I'm putting them out in the chat box right now. So once again, thank you very much, Professor Ashtekar. So let's all meet once again on 7th of November at 9 a.m. when we have a talk with Professor Heloise Stevens of the Auckland University, who'll talk about just space. So it's curiously titled A Space Talk. So I hope all of you enjoy. Thank you very much, Professor Ashtekar again. And thank you all of you for joining today's session. Hope all of you enjoyed.
Good night.
Thank you, sir. Have a good day.